Hello, everyone. Welcome back and Happy New Year. And this week we have Yuantian Yu. She's going to tell us some results on spectral Turán type problem.
Okay, thanks, Tina. It's my honor to be the first speaker of the new year. I'm Yuantian Yu from Central China Normal University. Now I am an international visiting graduate student in University of Waterloo. Today I will talk about some results on spectral Turán type problem. This is a joint work with Professor Shuchao Li, Wei Wei, and Yuantian Yu. My talk consists of the following 5 parts. Firstly, I will give some background. Here our topic is spectral Turán type problem. Then what is Turán type problem? In order to answer this question, and we need the following definition. Let H be a set of graphs. Graph G is H-free if G does not contain any element of H as a subgraph. In 2013, Fiorelli and Seminovic proposed the following problem. Given 2 parameters of graphs, say lambda1 and lambda2. For example, here lambda1 and lambda2 can be its order and size. Let H be a set of graphs and let G contains all H-free graphs with given lambda1. Here our aim is to maximize the second parameter lambda2 among graphs in G. For example, in this problem, if the given 2 parameters are order and size, then it corresponds to the classical Turán problem. That is, what is the maximum size of an H-free graph with odd n? The extreme value is always called Turán number of H and denoted by EXNH. The most well-known result in classical Turán problem is the Mento's theorem. It gives the exact value of the Turán number of C3, which is equal to the floor of the power of n over 2. And the unique extreme graph is the balanced complete bipartite graph. By this result, we can deduce the exact value of the Turán number of C3, C5, C2k plus 1. Since, as we know, if a graph is C3, C5, C2k plus 1 free, then it must be C3 free. So this value is no more than the Turán number of C3. On the other hand, since each bipartite graph contains no odd cycles, so this value is no less than the size of the complete bipartite graph. Then we can get the exact value of the Turán number of C3, C5, C2k plus 1. And the unique extreme graph is also the balanced complete bipartite graph. Here we shall notice that in both results, the extreme graph is bipartite. So next we want to consider what is the maximum size of a non-bipartite graph if it contains no short order cycles. And then adults answered this problem when G is C3 free. If G is a C3 free non-bipartite graph with odd n, then the size of G is no more than this value. And the equality holds if and only if G is this graph. In fact, it is obtained from the complete bipartite graph by subdividing one of its edge. And as a generalization, we consider graphs without short order cycles. We always call it the extension of the adult theorem. Assume G is a C3, C5, C2k plus 1 free graph with odd n. And if G is non-bipartite, then the size of G is no more than this value. In fact, in this result, if K is equal to 1, then it corresponds to the adult theorem. Here, the upper bound is sharp, since we can find a graph attains the maximum value. Notice that in this graph, it is obtained from the complete bipartite graph, and each part has size n minus 2k plus 1 over 2, and then replace one of its edge with a parse p2k plus 1. It is easy to check that the size of this graph is equal to this value, so we know the upper bound is stable. But in fact, I don't know if it is the unique extreme graph, so it is a question. Next, we are ready to introduce the spectral Turán type problem. In problem 1.1, if the first parameter is order and the second one is the spec radius of a graph, here we use lambda g to denote the spec radius of g. Then we have the following problem. What is the maximum spec radius of an edge-free graph with odd n? And we always call it Brody-Stohide Turán type problem. Since at first, Brody and Stohide propose what is the maximum spec radius of a graph with odd n. Then together with the Turán problem, that is, we add the condition G is edge-free. Then we have such a problem, and we call it by their names. For convenience, we also use a notation to denote the maximum spec radius of edge-free graph with odd n. Now we have two notations. One is the Turán number, and another one is the maximum spec radius. But what is the relation between them? As we all know, the spec radius of a graph is no less than its mean degree. That's 2 times the size of G over n, and which is equivalent to the size of G is no more than n over 2 times the spec radius of G, which implies the Turán number of H is no more than n over 2 times the maximum spec radius of an edge-free graph with odd n. So by the last equation, we can obtain, if we can get the exact value or an upper bound for the maximum spec radius of edge-free graph with odd n, then we can get an upper bound for the Turán number of n of H. I think it is also a reason why we want to study the spectral Turán type problem. And there are also a lot of known results in this field. For example, when the forbidden subgraph set H is equal to a complete bipartite graph, K copies of P2 and PK, and so on. Here, recall that in the Brody-Stohide Turán type problem, we consider graphs with fixed order. Next, we want to consider graphs with fixed size. In problem 1.1, if the first parameter is size and the second parameter is the spec radius lambda g, we have the following problem. That is, what is the maximum spec radius of an edge-free graph with size m? And we call it a Brody-Hoffman Turán type problem. The reason why we call it this name is similar as before. And there are also a lot of known results. For example, when H is equal to K3, Kr plus 1 cycles, theta graphs, and complete bipartite graphs. Until now, I have introduced some general background in our research. Next, I want to give the direct motivation of our research. In 2007, Bulbers and Nick Furrow posed the following conjecture. Let G be a Kr plus 1 free graph with order at least R plus 1 and M edges. Then the square of lambda 1 plus the square of lambda 2 is no more than R minus 1 over R times 2M. Here, lambda 1 and lambda 2 are the largest and second largest eigenvalues of adjacent matrix. This conjecture is still open. Until 2020, Ning and Wu confirmed this conjecture for R equals 2. In fact, it is the simplest case. The following is their result. Let G be a triangle-free graph with order at least 3 and M edges. Then the square of lambda 1 plus the square of lambda 2 is no more than its size M. And equality holds if and only if G is the blue up of H, where here H belongs to this set. Notice that a blue up of H is the graph obtained from H by replacing each vertex of H with a stable set, and we add all edges between two stable sets if and only if they are adjacent in H. For example, we consider P2. Firstly, we replace each vertex of P2 with a stable set IU and IV. Then since U and V are adjacent in P2, so each vertex in IU is adjacent to all vertices in IV. Then the obtained graph is a complete bipartite graph. Now we come back to our first result, theorem 2.1. By this result, we can deduce an upper bound for the spec radius of G. Since the square of lambda2 is non-negative, so we can deduce the spec radius of G is no more than the square root of M. And here, if this equality holds, we can deduce lambda2 is equal to 0. And then by computing all second largest eigenvalue of all extreme graphs, we can deduce. Here the equality holds if and only if G is a complete bipartite graph with size M together with some isolated vertices. In fact, this result was obtained by also before. Let G be a triangle-free graph with M edges. Then the spec radius of G is no more than the square root of M. With equality if and only if G is a complete bipartite graph with size M. Notice that the extreme graph is bipartite. That is to say, this upper bound is not set for non-bipartite graphs. So next, Ning and Wu consider non-bipartite graphs. Let G be a non-bipartite graph with size M. If G is C3 free, then the spec radius of G is no more than the square root of M minus 1. Equality holds if and only if G is C5. Clearly, this upper bound is less than the square root of M. So the upper bound in this result includes the upper bound in Nosso's result for non-bipartite graphs. And in the first two results, they consider graphs with fixed size. And their next result consider graphs with fixed order. Let G be a non-bipartite graph with order n, and if G is C3 free, then the spec radius of G is no more than the spec radius of this graph, with equality if and only if G is isomorphic to this graph. Here we use RK KST to denote a graph obtained from a complete bipartite graph KST by replacing one of edge with P2K plus 1. That is, it is this graph. It is obtained from a complete bipartite graph KST by replacing its one of its edge with P2K plus 1. Here K is equal to 1, so this part is P3. In this result, why they only consider non-bipartite graphs? Since as we know, if G is a bipartite graph, then it contains no odd cycles, so obviously it is C3 free. And as we know, in bipartite graphs, the balanced complete bipartite graph has a maximum spec radius, so it is not very interesting here. And then they only consider non-bipartite graph. Motivated by this result, then and the exterior of the Adolph's theorem, they propose the following open problem. Let K be a positive integer. How can we characterize all graphs among the set of C3, C5, C2K plus 1 free non-bipartite graphs with order n and has the maximum spec radius? Yet that is to say, what is the maximum spec radius among the set of non-bipartite graphs with fixed order and contains no short order cycles? In our research, we solve this problem. And we also have two more results about the adjacent eigenvalues of graphs without short order cycles. This result is our first main result, and we give a complete solution for problem 2.4. Here is our first result. Let K be a positive integer and G be a C3, C5, C2K plus 1 free non-bipartite graph with order n. Then the spec radius of G is no more than this graph. Equality holds if and only if G is isomorphic to this graph. This graph was introduced before. It is obtained from the complete bipartite graph by replacing one of its edge with P2K plus 1. Next, I will give a sketch proof of this result. Firstly, we assume G is a C3, C5, C2K plus 1 free non-bipartite graph with order n, and it has a maximum spec radius. So, in order to prove our result, it is first to show that G is isomorphic to this graph. And since G is non-bipartite, so it contains all the cycles. Here we let C be a short-lived old cycle of G. Since G is C3, C5, C2k plus 1, 3. So the length of C S is no less than 2k plus 3. Since C is the short-lived old cycle, so C is an induced cycle. Here, the first of our proof is to prove G is a connected graph, since otherwise G has at least two components, G1 and G2. Now we can add an edge between them and denote the obtained graph by G prime. Clearly, this edge is a cut edge. So G prime is also a C3, C5, C2k plus 1 free non-bipartite graph without n. On the other hand, as we know, the spec radius of a graph is larger than that of its proper subgraphs. So we can guess the spec radius of G prime is larger than the spec radius of G, which contradicts the fact that G has a maximum spec radius. So we can prove G is connected. Then since G is connected, we can use the Perrin-Frobenius theorem. There exists a unit positive eigenvector of G corresponding to lambda G, and here we use C to denote it. We let U be the vertex correspond to the largest coordinates in Z. Next, we want to partition the vertex set of G. Firstly, there is a cycle C and some vertices outside C. Then we want to partition the vertices outside C into two parts, according to it is adjacent to U or not. And we use X and Y to denote them. Then clearly the vertex set of U can be written as a union of X, Y, and C. Next, we prove our result by the following proposable cases. According to U lies in C or not, and X is empty or not. Here we only prove the first case, since the other cases can be proved by a similar discussion. Here we consider U is not in C and X is not empty. We want to construct the structure of G by the following three facts. We prove those facts by using a series of graph transformations and use the fact that G has a maximum spec radius and G contains no short-order cycles. Firstly, we can prove that the length of the cycle C is 2k plus 3. That is, there is a cycle C. There is a cycle C2k plus 3, and here is X, this one is Y. Since U is not in C and U is not adjacent to itself, so U is in Y, and U is adjacent to all vertices in X. And you may have some neighbors on the cycle C, but since G contains no short-order cycles, so U has at most two neighbors in C. In fact 2, we can prove for each vertex in Y, it has a common neighbors with U. That is to say, for each vertex in Y, it is adjacent to all vertices in X and has a common neighbor with U in the cycle C. Together with the fact that G is C3 free, so both X and Y are stable sets. In fact 3, we can prove each pair of distinct vertices in X has common neighbors in C. That is, for each vertex in X, it has common neighbors in C. But here I drew two neighbors, but maybe only one neighbor. Now we have such a structure of G. So our next step is to determine for vertices in X and Y, they have how many neighbors in the cycle C. we can get such a claim. By this claim, we can get each vertex in X has two neighbors in C, Ui and Ui plus 2. And each vertex in Y also has two neighbors in C, Ui plus 1 and Ui plus 3. We prove this claim by using the fact that G has a maximum stack radius and also use a lot of graph transformations. Now G has such a structure. Then we can draw the structure of G in another way. In this graph, X and Y are the same as before, and X and Y induce a complete bipartite graph. Here, each vertex in X is adjacent to Ui and Ui plus 2. Each vertex in Y is adjacent to Ui plus 1 and Ui plus 3. And besides those edges, there is a cycle C. Ui is adjacent to Ui plus 1, and it is adjacent Ui plus 2, Ui plus 3. And there is a path connects Ui plus 3 and Ui. In fact, this path is P2K plus 1. So clearly by this picture, we can know G can be obtained from a complete bipartite graph by replacing one of its edge with P2K plus 1. That is, G is isomorphic to this graph. Here, our last step is to determine the values of X and Y. Here, we can, by using quotient matrix and recurrence relations, we can get this claim. If T minus S is no less than 2, then the spec radius of lambda RK plus 1 T minus 1 is larger than the spec radius of RK T. Since T minus 1 minus S plus 1 is equal to T minus S minus 2, which is less than T minus S. So we can, by this claim, we can get if the difference between T and S is smaller, then the corresponding spec radius is larger. So to get with the choice of T, that is, G has a maximum spec radius, we can get G is obtained from the balanced complete bipartite graph by replacing one of its edge with P2K plus 1. So until now, we have proved our first result. That is, we can characterize the unique extreme graph among the set of non-bipartite graphs without n and contains no short-order cycles. As we said before, the spec radius of G is no less than its mean degree, which implies the size of G is no more than n over 2 times the spec radius of G. So to get with our first result, we can get an upper bound for the size of G if G is C3 C2K plus 1 free non-bipartite graph without n. Recall that in the extension of the Adolph's theorem, we also has an upper bound for the size of G, and we have tried to compare which bound is better. But in fact, in general case, we don't know which bound is better. And here we have two more results about the adjacent eigenvalues of graphs without short-order cycles. This result generalizes theorem 2.1. Let's keep a positive integer, and G is C3 C2K plus 1 free. Then the 2k's power of lambda 1 plus the 2k's power of lambda 2 is no more than beta 2k of G over 2. Here we use beta T of G denotes the number of closed T works in G. Equality holds if and only if G is the blow up of H. Here, H also belongs to this set. And by using this result, we can deduce an upper bound for the spec radius of G, since this value is non-negative. So lambda G is no more than the 2k's root of beta 2k G over 2. And by a similar discussion as theorem 2.1, we can obtain the equality holds if and only if G is a complete bipartite graph together with some isolated vertices. Also, the extreme graph is bipartite. So next, we want to consider non-bipartite graphs. Here, T is also a positive integer, and G is a non-bipartite graph. G is C3, C5, C2, K plus 1, 3. Then the spec radius of G is no more than this value. Equality holds if and only if K is equal to 1 and G is C5 together with some isolated vertices. Obviously, this value is positive, so this bound is less than 2K's root or beta 2kg over 2. And therefore, this bound includes the bound we obtained before. But in fact, as we know, the number of 2K's closed work, 2K closed work is hard to get. So we want to use an upper bound for it. Chen and Chen obtained an upper bound for the number of T closed works in G. And by using this upper bound, we can get another upper bound for the spec radius of G. Here G is a non-bipartite graph with size m and maximum degree delta. If G is C3, C5, C2K plus 1, we can get another upper bound for the spec radius of G. So until now, we have two upper bounds for the spec radius of G. Next, recall that if a graph G is C3, C5, C2K plus 1, 3, then it must be C3 free. Together with theorem 2, in theorem 2, they give an upper bound for the spec radius of G if it is C3 free. So this result also holds for C3, C5, C2K plus 1 free non-bipartite graphs. Then we have three upper bounds for the spec radius of G if it contains no short-order cycles. But which bound is better? In fact, we hope our bound is better. Next, we can give an example. In this example, it has 11 vertices and 11 edges. By theorem 2.2, we can get upper bound for the spec radius of G. It is no more than the square root of 10. And by using our result, we can get two upper bound for the spec radius of G. Both of them are less than the square root of 10. So for such a graph, we can get our bounds are better than theorem 2.2. In fact, we can give a family of graphs to show our bound is better. Here G is a non-bipartite graph, and it is C3, C5, C2K plus 1 free with size m and maximum degree delta. Here delta must satisfy this condition. Then by corollary 3.4, we can get delta G is no more than this value. And together with this value is no negative. So the second inequality holds. Then by using the restriction for delta, we can get it is no more than the square root of m minus 1. That is to say, for such graphs, our bounds are better than theorem 2.2. Now let us recall theorem 2.3 again. In this result, the equality holds if and only if K is equal to 1. That is to say, this upper bound is not sharp if K is greater than 1. So it is natural to consider, can we give a sharp bound for each integer no less than 2? And in fact, we hope we can get a better upper bound than theorem 2.2. And we have here we have an answer for K equals 2. We can see this result. Here G is a non-bipartite graph of size m, and G is C3, C5 free. Then we can get the spec radius of G is no more than this value. And by using the expression of beta 4 of G, the second equality holds. Here the equality holds if and only this equality holds if and only if G is C7 together with some isolated vertices. In fact, in theorem 3.3, if we let K equals 2, then we can get the spec radius of G is no more than the first square root of beta 4 of G over 2 minus 2. But in our result, it improved it by minus 5. And it is easy to get that this bound is no more than the square root of n-1. So this bond is better than theorem 2, the theorem 2.2. But if k is greater than 3, we have no idea until now. In this section, I have introduced some results about adjacent eigenvalues of graphs without short-order cycles. And in the next section, I want to introduce some results about the Brody-Hoffman-Turán type problems. That is, we fix the size of a graph. In this section, we only consider graphs with fixed size. So if I say G is a graph, it means that G has size n. Here we let F be a family of graphs and M be a positive integer. We use this notation to denote the set of F-free graphs with M edges and without isolated vertices. Firstly, Nick Foro consider graphs with maximum spec radius if it is KR plus 1 free. And in 2021, Li and Shu consider graphs with maximum spec radius if it is C5 free, C6 free, or K2R plus 1 free, and theta 1, 2, 2, theta 1, 2, 3 free. Or here, theta IJK is a theta graph formed by connecting two distinct vertices with three independent paths of lengths I, J, and K. Motivated by their result, we want to study graphs with maximum spec radius if it is theta 1, 2, 3 free or theta 1, 2, 4 free. And the unique and the extreme graph is a book graph, which is like this. It is a unique extreme graph. And here we recall the previous results. In the previous results, they only studied graphs with a maximum spec radius among the set of graphs with fixed size and forbidden some subgraphs. And the extreme graphs has particular structure. For example, in this result, the extreme graph is book graph, and in this graph, the extreme graph is a star. And in this result, the extreme graph is a complete bipartite graph. So next, we want to consider if G is not isomorphic to those special graphs, which graph has the maximum spec radius. That is to say, which graph has the second largest spec radius among the graphs with fixed size and forbidden some subgraphs. So in our following result, we consider this problem. Firstly, in this result, we consider graphs with the second largest spec radius if among the set of C5 free graphs, and this is C6 free graphs. This is theta 1, 2, 2, and theta 1, 2, 3 free. And the last result is a K2R plus 1 free. And the proof about the second largest spec radius is more complicated than the proof of the largest spec radius. And here I don't want to say more about it. Finally, I want to give some questions for further research. In section 3, we consider graphs without short order cycles, and in this conjecture, they want to give a condition to guarantee graphs contains consecutive cycles. Here, let G be a graph of sufficiently larger size M and without isolated vertices, and K is an integer. If the spec radius of G is no less than this value, then G contains cycles CL for every L less than 2k plus 2, unless G is isomorphic to this graph. In this value is equal to the spec radius of this graph. By the result in section 4, we can get, that is by theorem 4.2, we can get if k equals 2, then this result holds. But for k greater than 2, the conjecture is still open. And Next, it is the second conjecture. This conjecture was introduced before. Let G be a key R+1 free graph of order at least R+1 and size m. Then the power of the square of lambda1 plus the square of lambda2 is no less than this value. This conjecture was proved for R equals 2, but for R greater than 2, it is also open. In fact, this conjecture can be viewed as a generalization of another conjecture which was proposed by Edwards and Elphick. They conjecture that the spectral radius of G. They conjecture that if G is KR+1 free, then the square of lambda1 is no more than R-1 over R times 2m. Here we can find that first upper bound, those two upper bounds are equal. And this conjecture was proved by Nikiforov. Now we compare those two conjectures. It is natural to consider, can we give an upper bound for the sum of the squares of positive eigenvalues? That is, can we give an upper bound for... Here, P denotes the number of positive eigenvalues of a graph. The number of, it is still less than Is it still less than R-1 over R times 2m? In fact, it is not true, since we can consider C7. C7 is key 3 free, and it has 3 positive eigenvalues, but it is easy to check that for C7, the square of lambda1 plus the square of lambda2 plus the square of lambda3 is larger than 7. It is the size of C7. So this case is not true. But in 2021, Elphick gave another conjecture. Let K be a KR+1 free graph with size m. The square of lambda, the sum of the squares of lambda1, lambda2, and lambda_L is no more than this value, and this value is the same as before. Here, L is the minimum value of P and R. So they improved this case we said before. Here we only said P, but in their result, they choose L be the minimum value of P and R, and they want to say this conjecture holds. So they give some evidence for this conjecture. They proved it for weakly perfect graphs, Nisi graphs, Johnson graphs, and the classes of strongly regular graphs. In the last section, I gave 3 conjectures. I hope you are interested in at least one of them. Okay, that's all. Thank you for your attention.